is very important to make a very accurate decision in treating keratoconus patients. Because you all know that we have many options of treatment in keratoconus, like cross-linking plus customized laser treatments, intracorneal rings, but all of these depend mainly or basically on the refraction of the patient. And you know that the refraction of the patient is, in a keratoconus patient, is a little bit difficult. It is not that much hard if we know the tricks that I'm going to present now. So we have the tomography, then I'll show you how to do, of course, this will be very important for the optometrist rather than the ophthalmologist, but I do retinoscopy myself in my clinic. I'll show you how I do retinoscopy for a keratoconus patient, and then I do subjective refraction based on these two tools. Then I check the accuracy of my refraction by doing what's called over-refraction. We will see what is over-refraction. And then I do fine tuning and compare it with the real astigmatism of the cornea to validate my results. After that, I do binocular balancing. Well, if I'm going to prescribe glasses, if I want to prescribe glasses, I do binocular balancing to give the patient a comfortable glasses. And I do measurement of the potential visual acuity when the visual acuity is very low. So these are the steps, and we will start with the tomography. Of course, tomography is not only important for diagnosing the ectopic corneal diseases and classification of these diseases, but it is also very important for the refraction. Very important in the tomography is to look for the amount of astigmatism. I don't know, it is not clear here. However, this is called the total corneal refractive power map, the TCRP. It is very important. This is on the Pentacam, and there are similar maps on the Galilei and the Cyrus. So the TCRP is very important in order to know the amount, the real amount of astigmatism, of corneal astigmatism. I do not depend on the astigmatism given by the SINK, the K1 and K2, in calculating the amount of astigmatism, because SINK is very limited. It depends on the ring, not on the zone over the pupil, and it is at 3.2 millimeters rather than the whole visual field of the patient. So I see the zone, the amount of astigmatism over 5 millimeter zone, 5 rather than 3, and I see it in zones centered with the pupil center rather than the apex or the center of the cornea. So this is the total corneal refractive power map, giving me the K1 and K2 and amount of astigmatism, 5 millimeter central zone. How I do retinoscopy, I will show you the following video. But before, why not to depend on autorefractometer? Actually, the worst device that has been ever invented, is the autorefractometer. We should not depend on the autorefractometer, neither for either for the glasses in normal people or in keratoconus, because of the calibration. You know that it is calibrated based on the ratio between the anterior and posterior surfaces of the cornea. If there is any change in this ratio, like after keratorefractive procedures or in keratoconus patients, it will not give you any accurate number. In addition, it initiates accommodation, so I cannot depend on it, because there is what is called near awareness, the neuro awareness of near objects, even if the target is calibrated to seem as it is far. In addition, the astigmatism changes when we do cycloplegic refraction. When we do cycloplegic refraction, the amount of astigmatism on the autoref is not like the one before cycloplegic refraction. In addition, I cannot do over-refraction with this tool. The over-refraction is, I want to check the accuracy of the glasses. I cannot do it with the autorefractometer. The only thing that can be given by the autorefractive keratometer is the K readings, which is like SIM-K because it is placebo-based. However, tomography is much better. So there is no single reason to use the autorefractometer in refracting any patient, not only in eclectic corneal diseases. I'll show you now how I do retinoscopy, what are the positions and the tools I use in my clinic.
Successful retinoscopy for a patient with keratoconus. Actually, to do this, we have 3 tools. The first tool is the retinoscope itself. Now, for the retinoscope, as you see, it has a sleeve. Now, this sleeve can be in 2 positions, either the lower position or the upper position. Now, the lower position will give us the convex mirror, the convex mirror. Now, the convex mirror will show me with movement for hypermetropia and against movement in myopia. Now, if I move the sleeve upward, it will give me the concave mirror, which will give me against movement in hypermetropia and with movement in myopia. Although the reflex, the light reflex, is sharper and clearer with the concave mirror, but I usually use the lower position of the sleeve, which gives me the with movement in hypermetropia and against movement in myopia. Now, the second tool is the lenses. As you see here, we have 2 types of lenses, the separate lenses and the bars. I usually use the bars. I don't recommend using separate lenses while doing the retinoscopy. The simple reason for this is like this. If I come to the patient and start doing the retinoscopy with the lenses, I will change from one lens to another one in front of the patient. And this movement will attract the attention of the patient, which will initiate his accommodation, especially if the patient is a child. So I want the patient to concentrate on the target, which is the third tool that I'm going to talk about later. I want the patient to concentrate on that tool and do not move his eye, let him to initiate his accommodation. So I usually use the lens bar. As you see, I can use the lens bar very smoothly. I can switch from one lens to another one without letting the patient pay attention to this. So this is the second tool. The third tool is the fixation target, which is the flower for children or the big letter, E letter, for the adults. Now, I want to concentrate on the distance for this fixation target. It should be the standard distance, which is from 4 to 5 meters. I don't recommend those machines which are put in front of the patient and the size of letters are adjusted just to mimic the distances. And because of small rooms or small clinics, you may find the projector itself adjusted for 2.5 meters and the sizes of the letters are adjusted to do the same job. Now, actually, I don't recommend this. Why? Because it is not only the size of letters that fall on the retina, but it is the neuro awareness of the near objects in front of the people. When I see a near object, I have accommodation, even if the object is very, very big, because of the neuro awareness of the near objects. So I recommend to use the standard distance, which is 4 to 5 meters. Now, after these 3 tools, we have the final step, which is the final thing to talk about, which is the position that the physician should take when doing the retinoscopy. Now, as you see, if I want to check the right eye of the patient, I will use my right hand and I will use my right eye. And I will sit paraaxial just to stay away from the visual axis of the patient. And after that, I can switch to the other eye by using the retinoscope in the left hand, and I will check the left eye of the patient by my left eye. In this position, I will say paraaxial to stay away from the visual axis of the patient, and I will do the retinoscopy smoothly. Now you may ask the question why I don't do retinoscopy on the left eye while I'm staying on the right side. Actually, this is wrong, because if I'm checking the left eye, I'm not checking the visual axis or the paravisual axis. I'm checking the mid-periphery of the retina, which is closer, and this will give me a hyperopic shift in the result. That's all. Thank you very much.
Okay. Now I start the retinoscopy by aligning the streak, as you see, the light streak. And when I move the streak in this position, it means that I am checking this meridian, the power of this meridian. And the axis of the streak is the axis of the correcting lens. So, for example, if I have -3 at the meridian of this meridian, and the axis is 70 of the streak, it means that I need a correcting lens, concave correcting lens, -3, and the axis of the lens should be at 70. In retinoscopy, we determine the most accurate axis, and then we determine the power. How to determine the most accurate axis? We all know that we have scissoring reflex, which is the earliest clinical sign, and sometimes it may precede the topographical changes. So, suppose I have scissoring reflex in this direction. I go to another direction, which gives me a clearer streak, inner streak. And I will try to take a position of the streak or to align it on an axis that makes the outer streak parallel with the inner reflex. After that, in order to make it sharper, I use minus lenses usually, because usually the ectatic corneal diseases are associated with myopia. But in some cases, like pellucid marginal degeneration, you may have hypermetropia. However, so to make it clearer, I use, for example, -2, and I will check the alignment of the outer and inner streak. I will find a break. When the axis is not accurate, I will find a break. Now, I will try to align them to overcome this break by moving the streak, the axis of the streak again, in a direction until they are aligned completely. And this will be the axis of the correct axis of the streak the streak. And on the frame in front of the patient, I can see which axis is the most accurate one. After that, I determine the power by changing the power of the lens, the correcting lens, in order to reach the neutral point. When I reach the neutral point, as you know, we will have a wide and dim inner reflex. So, for example, the power is -3.5. The power -3.5 on this axis means that we are checking this meridian. So I need a correcting lens of -3.5 at 110 in order to correct this meridian. The subjective refraction. The subjective refraction depends on determination of the incorrect visual acuity. Then I start 2 lines above it. Then I use the slit lens to determine the axis and then to determine the power. For example, the incorrect visual acuity of this patient is, suppose this line. I start 2 lines above, and then I use the slit lens. The slit lens, I put it very near to the meridian that I have been checking, and because this is the most accurate meridian, actually, or the most the clearest meridian. Then I ask the patient, either I ask the patient to move it or I move it myself very slowly to ask him which position is the sharpest position. Suppose it is the 30 degree. It means that, suppose it is the 30 degree. Now, it means that I am using the clearest, or the patient is using the clearest meridian to see. It is the 30 degree. And the slit lens is hiding the other meridians, which are very irregular. After I adjust it at the 30 degree, Then I start adding lenses in order to reach the best correct visual acuity. And suppose it is the patient reached the best correct visual acuity with the -3. So it means that he has -3 on this meridian. After that, I rotate the slit lens to the opposite position, which will blur his vision, because in this position he is using the very irregular axis. And I do the same by adding spheres. Suppose the patient reached this letter by the -5. So he has -5 power at this meridian and -3 power at this meridian. In order to translate this into an equation, it means that we need to use -3 sphere with -2 cylinder, but the axis of the cylinder should be this meridian in order to give its effect on this meridian. So the patient has -3 diopter sphere, -2 diopter cylinder at 30. So the patient has -3, -2 at 30. We come to over-refraction. Now, what is over-refraction? With the lenses in the frame, I do retinoscopy in order to check whether the power, whether the axis, to be accurate, the axis of the lens by doing the vertical and horizontal retinoscope. It is not necessary to use the same axis, but horizontal and vertical. When the let's say, when the axis is not accurate, this is when the axis is very accurate. You will find the streak, inner and outer streaks are aligned. But when the axis is not accurate, suppose this axis, you will find that the streak is broken. And you will find yourself, you will need to change the position of the cylinder in order to make the two axes or the two streaks aligned. That's it. Fine-tuning, I do fine-tuning by using the cross cylinder. As you know, we have 0.25 power, we have 0.5 power, we have the 1 diopter power. The worse the visual acuity of the patient, the higher the power that should be used. Suppose I wanted to fine-tune the axis of this patient. I use, for example, the 0.5. I align the handle aligned with the axis of the correcting lens, the cylinder lens, and then I'll do the movements. As you know, I will flip it, and then I will ask the patient which position is clearer. And suppose the patient says this position is clearer. Because he has minus, I will move the axis of the minus towards the minus sign on the cross cylinder. And then I will repeat the same, but after I move the handle again to the new position of the axis. For the power, I will align the signs with the axis rather than the handle. And I do the flip and ask the patient which one is better, and I modify this accordingly. Suppose the patient is better with minus 1.5 diopters. Then I do the red-green balance by changing the sphere itself. And let us say that the red-green balance is okay when the patient has minus 2.75. Now I come to the very, very important aspect, which is the corneal power, the corneal power. Before I go through the corneal power, I'll give you an introduction to the types of maps and how they measure the power of the cornea. We have the anterior sagittal curvature map. All of us know this, and we use it when we screen for keratoconus. Now, the anterior sagittal curvature map uses the principle of tangents at points that should be measured, and this piece AB is considered as the radius of curvature at this point, and accordingly we apply the equation to derive the power of the point at this point. But as you see here, this curvature map uses the wrong index of the cornea. It uses the 1.3375. Okay? The other one is the anterior tangential curvature map. It uses principles of the best fit circles in the points that should be measured, and the radius of those circles is considered the radius of curvature and put into the equation. But again, the refractive index is 1.3375, which is the wrong one. The anterior refractive power map uses the principle of ray tracing, but it uses the 1.3375. The true net power, it calculates the anterior and posterior surfaces together, but it does not consider corneal thickness. And it uses the real refractive index of the cornea. The equivalent K-reading power map, also it uses ray tracing, but it does not consider the thickness, and it uses the correct index of the map of the cornea. Then we come to the total corneal refractive power map, which gives us the real refraction of the cornea, the real power of the cornea. Why? Because it uses ray tracing, it uses the correct index of the cornea, and it takes into consideration corneal thickness. So this is the only map that can give you an idea about the power of the cornea. Now, okay. Is it working now? Working? Already working. Okay, inshallah. Now, how I'm going to use this map in my calculations. Just to remind you, I am using the zone, 5 millimeter zone centered with the pupil center in the total corneal refractive power map in order to know the amount of astigmatism and to know the K1 and K2 of the cornea, because these are the most accurate Ks and most accurate astigmatism in the cornea. I'll show you now.
Refraction. First of all, the astigmatism is the K2 minus K1 difference. In order to calculate corneal refraction, first we need to push K1 towards K2 by a plus cylinder. The axis of the cylinder is the K2 axis. After that, we have to push both K's towards the neutral point by a sphere. I'm going to apply these rules on 3 clinical examples. Example number 1. A patient has K1 37.5 at 180 and K2 40 at 90. So the flat axis, this is the flat axis and this is the steep axis, but both are flatter than the neutral point, which is 43.5. Both are below this point.
Let me stop at the neutral point. What is the neutral point? The average K reading in the normal people in the center of the cornea is 43.5 diopter. The average normal K in normal people. So I'm going to use this neutral point, this point, I'm going to use it in order to refer all the K readings in my example and to show you how I calculate the refraction of the cornea accordingly.
one is the astigmatism. In this example, it is 2.5, which is 43.5. Both are below this point. Now I'm going to plot this on the scale. This is the neutral point, which is 43.5. This is K1, and this is K2. Now the difference between K2 and K1 is the astigmatism. In this example, it is 2.5 diopters. Now, K2 differs from the neutral point by 3.5 diopters. So this is the geometrical illustration. As we see, the difference between K1 and K2 is 2.5 diopters, which is the astigmatism, and the distance between K2 and the neutral point is 3.5 diopters. Now, back to this scale. We have to apply the first step, which is we push K1 towards K2 by a plus cylinder. So I'm going to push 37.5 towards 40 by a plus cylinder. Why plus cylinder? Because I want to increase the power of this flat axis to be same as 40. So I'm going to use plus 2.5 cylinder. After this, both axes will be the same. They will be 40. So now the distance between the resulting axis and the neutral point is 3.5. Now I'm going to push this resulting axis towards the neutral points by another plus sphere. Why it is plus? Because I want to increase the power of 40 to be same as the neutral point. So I'm going to use plus sphere. Now what is the axis? The axis is the axis of the K2. So the equation here is plus 3.5 sphere plus 2.5 cylinder at 90. Now I want to check whether this is right or not. I want to use a plus cylinder oriented parallel to the 90 degree, and this is correct because the action axis of this cylinder is the 180, and I need it like this because I want to increase the power of the flat axis to be as 40. After that, I want to push both axes towards the neutral point by a plus sphere. Example number 2. A patient has K1 45 at 90, K2 48 at 180. So we have the flat axis 45, and this is the steep axis, and both are steeper than the neutral point. Now I'm going to plot this on the scale. This is the flat axis 45, and this is the steep axis, and the difference between the flat and the steep is 3 diopters, which is the astigmatism, and the distance between the K1 and the neutral point is 1.5 diopters. So this is the geometrical illustration. We have 48 is different from 45 by 3 diopters of astigmatism, and the flat one is away from the neutral point by 1.5 diopters. Now back to the scale. I have to push K1 towards K2 by a plus cylinder because I want to increase the power of the flat K. And then the resultant K will be away from the neutral point by 4.5 diopters, as you see, because 48 minus 43.5 is 4.5 diopters. So I got 2 steep axes, they are 48, and they are away from the neutral point by 4.5 diopters. So here it comes the second step, which is I need to push the 48 towards the neutral point by using a minus sphere. Now why it is minus? Because I want to reduce the power of this 48. So it will be minus 4.5 sphere plus 3 cylinder, and the axis of the cylinder is the K2 axis. Now I want to check whether this is correct or not. Minus 4.5 plus 3 at 180. So I need to use a plus cylinder oriented at 180 in order to get its power on the 90. And this is correct because I want to increase the power of the 45 to be as same as 48. After that, I want to push both towards the neutral point by using a minus 4.5 sphere. Example number 3. A patient has K1 40 at 180, K2 45 at 90. So geometrically, this is the 40 and this is the 45. Now this is mixed astigmatism because one is below the neutral point and one is above. To plot this on the scale, this is K1 and this is K2. Now the difference between K1 and the neutral point is 3.5 diopters, and the difference between the K2 and the neutral point is 1.5 diopters. And the difference between K1 and K2, or let us say K2 minus K1, is 5 diopters, representing the corneal astigmatism. Now I need to push K1 towards K2 by using a plus cylinder. Why plus? Because I want to increase the power of the 40 to be same as 45. So it will be plus 5. Now, after this, both will be 45, and both will be above the neutral point by 1.5 diopters. Now I need to push both towards the neutral point by using a minus sphere. Why minus? Because I want to reduce the power of the 45 to be same as 43.5. So I'm going to use minus 1.5 sphere plus 5 cylinder, and the axis of the cylinder is the K2 axis. Now to check this geometrically, I need to use plus 5 at 90 in order to get its power on the 180, in order to increase the 40 to be same as 45, and then I need to push both to that neutral point by using minus 1.5 sphere. So in summary, the K2 minus K1 difference is
now, as we saw now, we want to calculate the refraction of the cornea. Now, I need to translate this refraction of the cornea to glasses. Why? Because I want to compare between the corneal refraction, as you saw in a while, with the manifest refraction. And the manifest refraction is usually on the level of a glasses. So how I will transfer or translate the corneal refraction that I calculated now into glasses. Now, the principle of this is very simple. There are two paths: the inward translation from glasses to cornea and the outward translation from cornea to glasses. Let us start with the first translation or first path. Let us call this corneal manifest refraction. This, the one that we saw in the video, let us call corneal manifest refraction. We all know that each 1 diopter of correction by laser correction changes K readings by 0.8, roughly by 0.8 diopters. So minus 1 at glass levels will change the K readings on the corneal level by 0.8 diopters. And for hypermetropia, each 1 diopter at the level of glasses will change the K readings, will increase the K readings by 1.25 diopters, roughly. So I'm going to use this in the translation. Again, each one diopter changes, reduces the K reading by minus 0.8. So if I have minus 3 diopters at the level of glasses, it will make a change at the level of the cornea of minus 2.4 diopters. So the manifest refraction will be translated into corneal manifest refraction using this. Minus 3 at the level of the glass is minus 2.4 at the level of the cornea. And vice versa. Minus 2.4 at the level of the cornea should be multiplied, because it is minus, by 1.25. Okay? This, the first path, 0.8, and the opposite path, 1.25, to have the manifest refraction. In the hyperopic correction, the opposite is the true. Each one diopter of correction will increase the K readings by plus 125. So if I have plus 3 diopter sphere, if I correct it, it will increase the amount of refraction at the level of the cornea by 3.75. It will be 3.75. So the 3 at the level of the glass will be translated into 3.75 at the corneal level, and in the opposite path, it should be multiplied by 0.8 to translate the corneal manifest refraction into manifest refraction. So the one I used was corneal refraction. The one I calculated by the total corneal power, refractive power map, was the corneal refraction, and I want to translate it into what is called corneal manifest refraction at the level of the glasses. I will multiply myopia by 1.25, and I will multiply hyperometropia by 0.8. This is the principle of how to translate corneal refraction calculated from the total corneal refractive power map into glass power. This is the neutral point, and let us have some examples depending on average K, just to simplify the things. This is the average K, the normal average K. If the average K is less than this, the cornea is flat. And if it is above than this number, the cornea is steep. So it is supposed that the patient has hypermetropia when the cornea is flat and myopia when the cornea is steep. This is logic. So, for example, a patient has average K 46.5, so he has myopia. And the difference between these two is minus 3. And because it is minus, I have to multiply it by 1.25 to translate it from corneal refraction into corneal manifest refraction at the level of glasses. And the patient has minus 3.75 diopter of spherical equivalent. A patient has 41.5. The difference is plus 2. And because it is plus, I want to multiply it by 0.8. So the patient has corneal manifest refraction of plus 1.6 diopters. Now I come to this point, which is comparison between the manifest refraction I did for the patient, either for refractive surgery or in keratoconus patient, and I need to compare this manifest refraction with the corneal manifest refraction following the previous steps. Okay? So as you see, according to the corneal manifest refraction, the patient has, because of high K readings, as you see for this example, the patient has minus 8.25, minus 2.5 diopters at 30, and the manifest refraction is minus 2.75, minus 1.5. Now, when I have manifest refraction less, the sphere is less than the corneal manifest refraction, this can be explained by an internal component. Maybe he has a flat lens. So there is an internal component that can compensate, or the axial length of the eye. So that it is not a surprise. But the problem is when we have manifest refraction, manifest sphere is higher than the corneal manifest sphere. In this case, we have to do cycloplegic refraction for the patient because most probably he has accommodative spasm. For the cylinder, the corneal manifest refraction enables me to check the axis, to match the axis and match the power, because maybe I will bring the patient back to the chair and examine him again using this, the corneal manifest astigmatism. And maybe with the corneal manifest astigmatism, he can see better than what I did by the manifest refraction. So this is why corneal manifest refraction is important, because I need to validate my refraction. The last point is the binocular balancing. When I want to prescribe glasses for a patient, I need to do binocular balancing. I cannot give the prescription, especially in irregular corneas, I cannot give the prescription as it is to the patient, because there are the aberrations of the lenses, especially when the axes are oblique. Now I'll show you how I do the binocular balancing. We have these 4 tricks: the vertical, horizontal manipulation, the parallel manipulation, and then manipulation of sphere and manipulation of cylinder. The vertical horizontal manipulation. Let us have this example. This patient has in his right eye minus 275 sphere, minus 1.5 diopters cylinder at this axis, and he has, this is oblique, and he has in the left eye horizontal axis, as you see. Now this patient may be not comfortable with these glasses if I prescribe it as it is. So what I do, vertical horizontal manipulation of the axis. I just try to approximate the axis towards either horizontal or towards vertical. I will see if I change the axis of the lenses, is the patient more comfortable without reducing the best correct visual acuity so much. I can reduce it by 1 or 2 lines and keep the patient comfortable better than give him very sharp vision, but he is not comfortable. This is the vertical horizontal manipulation. The other manipulation is the parallel. I will try to make both axes parallel to each others. Like this one, I will rotate this one. Maybe if I rotate it to be parallel to this one, maybe the patient will be very happy with this. After I change the axis, I manipulate the axis and I find which axis is better for him binocularly. I have to manipulate the sphere, because after this manipulation, the sphere may overcorrect him. So I may reduce the amount and then I manipulate the cylinder binocularly together in order to give him best visual acuity and most comfortable. Finally, potential visual acuity should be measured when the patient has corrected visual acuity is not that good, 0.6 decimal or less, and we should use hard contact lenses, or maybe now the next speaker will be much better than me in explaining the importance of this point. And this point is very important because, for example, if a patient has 0.4 diopter corrected visual acuity, and he is keratoconic patient, I want to know whether intracorneal rings will give him a benefit or not. I want to know whether the topography guided treatment will give him a benefit or not. So I have to check his potential visual acuity and make my decision accordingly. Thank you very much, and I'd like to announce for my new book, which is now in the market, is Corneal Crosslinking with Arthur Kemming. Thank you very much.